Hello everybody, how are you guys today? So today we are going to be looking at some 5 statements that make every LARPer angry, right? So a LARPer is someone who just pretends to know about the subject instead of actually learning about it, when in reality they're just experiencing the Dunning-Kruger effect. So let's take a look at the first one. So for the first statement is 0.999 recurring, which just means it goes on to infinity, is equal to 1. Now, a lot of people that don't really understand the subject will tell you that no, it can't equal 1. It's very close to 1, but it isn't 1. That's impossible. So I'm going to show you 2 proofs today that will show you that 0.99 recurring directly equals 1, no more, no less. Let's start with the number line proof. So if we draw a number line from 0 to 1, and we have, for example, 0.5, it will be directly in the middle between these two. If we plot something like 0.75, which is the average of these two numbers, you'd have it in the middle of these two. Now, if we had a number 0.9, you'd see it right about here. Very, very close to 1, not exactly 1. Now, if I had a number like 0.99, you'd see it 99% of the way. Really, really close. Now, let's say I have 0.99999, as close as can be. Then there is no way, as I could do with 0.9, for example, sorry for going back, 0.9, I can do 1 minus 0.9. There's always a difference between these two numbers. But when I go for 0.99999, you cannot name me a single number that is in between 0.99 recurring and 1. So that is the first statement, that it must be true that 0.99 is equal to 1. For my second statement, we'll assume we don't know the value of 0.99 recurring. So we'll set 0.99 recurring equals to x. Now we want a way to somehow get rid of the 99 recurring and have a whole number of values so we can find it as a fraction. So there's a very popular method, and we'll just apply that directly. We start with multiplying by 10 on both sides, so we have 9.99 recurring equals to 10x, right? So now our second step would be to remove the recurring part. So we can subtract from both sides 0.99 recurring, and we know that 0.9 recurring is just x, so we have 9 equals 9x. Now logically, what should x equal? X equals to 1. So this is the second proof for 0.99 recurring equal to 1, completely given. Now, for my second statement, which is also true, is that a negative number times a negative number equals a positive number. Now, a lot of people know this, but they don't know why it happens. They just memorize it. So I'm going to prove it to you today. So we'll start with our statement that negative a times negative b equals to AB, where A, comma B are greater than 0. So if these are greater than 0, and this is a negative number, this is a negative number, and this is a positive number. So minus, minus, plus. So we'll start with some algebraic manipulation. We'll start by saying that 0 equals B plus the negative variant of B. So B plus minus B equals 0, which makes sense, everybody knows that. So what we'll do next is we'll multiply both sides by negative A. Just bear with me. Multiply both sides by negative A, so we have negative A times 0 equals negative A into B plus minus B, all in parentheses. Now this simplifies to just 0, and then this equals negative AB plus negative A times negative B. Right? So we see our terms are like terms. We have negative a times negative b, and that's what we want to isolate. So what we can do is we can add ab onto both sides. So we can have ab plus 0 equals ab minus ab plus negative a times negative b. What we can do now? These two go out together, is equal to 0. So we have our final statement, ab equals negative a times negative b, which is our original claim. And since a and b are greater than 0 and ab is greater than 0, a and b separately are greater than 0, that means negative a times negative b equals positive AB. Okay, for my third statement, I say that you need 23 people in a room to have a 50 or a close to 50% chance of sharing the same birthday, which against all our intuition is actually true. So let me write down some statements we need to know, some things we need to know as well. So we're gonna have some assumptions. We're gonna assume that already no one shares the same birthday. There are no people that everyone has a unique birthday, and that the probability that someone doesn't share a birthday plus the probability that someone shares a birthday must equal 100%. So we're gonna have, say, S of H, right, to share a birthday, plus S of NH, no sharing birthday, equals 100%, which is a true statement. The probability of something not happening plus it happening must equal 100, since 100 is the limit, right? So we're gonna draw two poorly drawn people and assume these people have different birthdays. So let's say this person has a birthday July 2nd, July the 2nd. Okay, person has a birthday July 2nd. So the odds, if we ignore this person, the odds that they share a birthday with the other person in the room is what, 365, since they have all days, over 365. Ignoring this person, of course, since they're the only person in the room, the odds they share their birthday with themselves must be 100%. Now, if we factor in birthday X, right? How many days are left? Since every birthday must be unique, there's only 364 days left for that person, since excluding leap years, obviously. Over 365, right? We've decreased by 1. And this gives you a relatively high probability, I don't know, almost equal, a high chance that they don't share birthday, right? Remember, we're solving for S of NH, no sharing birthday, right? So you'd say, okay, we need this to equal 50%. How to equal it 50? When does it equal 50? Why does it equal 50? Let's go. We can write down 365 over 365 times 364. I'm not going to bore you with this. 364 over 365 all the way down to about, I think it's 343 over 365 equals a roughly, very roughly 50%. It's actually somewhere closer to 49.7 something percent. I'm not sure actually. 7%. That someone does not share birthday. Now, how many people is this? It's just 23 people. It's 23 people, of course, because we can't include the initial term, which is 100%, which is just 1. So this is 23 people between these two, right? So that's it. This is the probability that people don't share the same birthday. So we do our original statement. We're going to bring this over back onto here. We're going to have that people share a birthday, S of H equals 100% minus S of NH. So we have 100% minus 49.7%. And this, again, roughly, because I'm not sure of this number, equals 50.3% chance that people share the same birthday. Like this, horizontal asymptote at 0, and we have it sloping down. Now, Gray-Beul's horn is specified from 1 to infinity, right? Approaching the left-hand side of infinity. And once you draw it out, it kind of looks something like this. Excuse the drawing, it's kind of bad. Very bad, actually. Very bad drawing. But it stretches on to infinity, so logically, you shouldn't be able to fill it, nor you should be able to actually cover it in paint. Now, I'm going to use a logical statement, and I'm going to use a mathematical statement, a mathematical proof of it. We know that the volume is decreasing over time. You can see the volume if we took it from the side, that the volume would be decreasing as we went down. So then we'd have it somewhere around here. We'd have it like this. It's more curvy, more curvy. The volume would eventually decrease so much, right? It doesn't actually breach an end, but it decreases a lot, right? Whilst the surface area continues on growing. Not only on this side, but on all sides, the surface area continues on growing to infinity. While the volume gets smaller, the surface area keeps growing. Therefore, we can fill it up, but we can never actually cover it. Now, for the actual algebraic proof, the calculus proof, is we need to know two formulas. The volume of any function, right, is pi times the integral bound set from a to b of f of x squared in terms of dx, right? So now we can just basically solve this as basic algebra. We have pi times 1 to infinity of 1 over x squared dx. We have this equal to pi to 1 to infinity, blah, 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 x negative 2 dx. This equals our bound, pi, x negative 1 over negative 1 from infinity to 1. Then we move down, and we can see that anything x infinity in the denominator, so we have pi into negative 1 over infinity minus, so it's just plus negative 1 over 1 in the denominator, and we know this just equals 0, pi, negative pi. Doesn't make sense. Why doesn't make sense? Apologies, I realized that I already made this positive, so this should be positive, so this just equals pi, because the units cubed. Now, on to the surface area, and I'm going to tell you a little story about the surface area before we start. Is that the surface area formula, it actually has something to do with the length of a function formula. And the length of a function formula, I found it myself in school once, although the proofs for it was already published. I found it myself. So one day I came up to my friend and I said, why can't we derive the area of something in meters squared to get its length? Shouldn't we be able to, since the derivative of m squared would be 2m? And he's like, well, let's see. We tested on a couple triangles and it worked for some, but not for all. That means my statement was false. It actually worked on a 3, 4, 5 triangle, which I found really, really cool. So I told him, you know what, by the time you go to your exam and come back, I'm going to find a formula for the length of any function. And he said, I challenge you to find it. And he came back and I showed him, boom, this is my proof. So before we start onto the surface area, I wanted to start with the length formula. I wrote a poem about it, and I'm really proud of this actually. It states that the derivative of a function squared plus 1 and the square root of its sum in an integral from a to b will give you the length it becomes. Now, what did I just say? The derivative of a function squared plus 1 and the square root of its sum in an integral from a to b will give you the length it becomes. There you go. There's our derivative function squared plus 1, square root, ab will give you the length it becomes. Now, that has really nothing to do with what we're doing right now, but it plays part in the surface area formula. And the funny part about this is once I was on a date, and I was kind of daydreaming about math, like while going down the escalator, and I was like, okay, I have the length, why don't I have the surface area? I'm just thinking and thinking, I'm like, okay, in reality, the surface area would just be a bunch of tiny cylinders. So what do? You just find those. So it's 2 pi. So if you know this formula for the surface area of a cylinder on the outer part, ignoring the two circles on the top and bottom, you have 2 pi RH. Now what would R equal? That would just equal our function. Not squared, sorry. Our function, right? Because the radius depends on, if we draw it over here, the radius depends on our function. Times the length, because it's 2 pi h. The length would just be this. So we can put it as L in terms of dx from A to B. Wow, incredible. And this is our surface area. Okay, so we came to the statement that 2 pi into f of x, which is, first of all, from 1 to infinity, times 1 over x, which is our function, times the length formula, boom, 1 plus the derivative of this. Oh, that's so complicated. And I think it's negative 1 over x squared. Would be negative 1 over x squared. Maybe, yeah, negative 1 over x squared. So it's really complicated. Oh, now please don't think I don't know the proof. I have it on my paper right here. But I really didn't want to bore you guys out with solving this. So you'd end up with 2 pi times the natural log of e of x from infinity to 1, or 1 to infinity, and this just equals infinity, right? I didn't want to go through all the steps. I have another videos for integrals and whatnot. Just trust me, basically trust me, that this actually diverges and we don't get a finite value for the surface area of this. This is the proof for Gabriel's horn. And now on to my last statement, that some infinities are bigger than others. Right? So some people usually represent it as infinity plus 1 is greater than infinity, but this is kind of hard to understand, so I'm going to show it in a more visual way. Let's say from 0 to 1, if we refer back to the number line at the beginning of our video, from 0 to 1, you can pick out an infinite amount of numbers between these. You can pick out an infinite amount, right, of numbers from 0 to 1, whether it's 0 0.1, 0 0.2, 0 0.11, 0 0.111, 0 0.157, 8,000, whatever, it doesn't matter. You can pick out an infinite amount of numbers in between 0 and 1. And that's one infinity. You can say that the infinity equals n. Now let's say from 0 to 2, right? On the number line, let's say we go from 0 to double the length, 2. Could you not pick out more infinities from here? There are more numbers because you have the first set of infinity, which we described as n, and you have another set which we described as n. I don't want to combine them and make them 2n and say infinity equals 2n because that's kind of a stupid statement. But you could pick out more infinity numbers from here than from here, which shows us that some infinities are in fact larger than others. Or as we like to say, some sets of infinity are larger than others. And thank you for watching. These were my 5 statements that makes any LARPer of math mad. And I am Murda's Math. Thank you for watching again. Goodbye.